Okay, so we'll get started. Okay, all right. So a couple questions came in the chat, and so first is the final cumulative? And the answer is sort of. As far as like calculation questions go, it's going to be stuff after the midterm, but there will be. Well, I don't know. I mean, some of the concepts are like build up on each other, right? Like in chapter 9, in your homework problems, it presented data, and you had to be able to calculate the mean of your data and the standard deviation of your data, and so that's technically an older concept, but I think that's like a fair question to ask. So, but you know, as far as the calculation questions go, it's going to be mostly chapters 7, 8, and 9. But there might be like definition / conceptual questions that come from the earlier chapters. So you know, as far as it being cumulative, I might ask questions that come from the earlier chapters, but they won't be calculation in nature, right? So I won't be asking you things like you know, find the regression equation or something like that. I won't say like, here's some numbers, find the regression equation, what's the prediction that the regression equation would make. But I might ask a question like, you know, what does correlation measure? And you would talk about, you know, correlation tells us the direction and strength of a linear relationship or something like that, right? So it might be definition based, but / concept based, but not calculation based. Okay, is Gradescope Quiz 0 still counting as extra credit? Yes, I always have a little bit of trouble with the gradebook regarding how to enter extra credit properly. So, but yes, Gradescope Quiz 0 will count as extra credit. Will we be getting our Quiz 4 grade back before the final? So yes, I've talked to the graders. So Quiz 2 and Quiz 3 were posted this weekend, so you can see those. Quiz 4 will get graded, I'm hoping by Wednesday, okay? And you know, I got some emails about Quiz 4, and I'm sorry to the students I haven't responded to. In general, on the weekends, I'm very bad about responding to emails. I take my weekends as weekends, so I try to set clear boundaries between school and or like work and life. So on weekends, I'm very slow to respond. So anyway, as far as Quiz 4 goes, or any of the quizzes that go, I know some of you struggled with Quiz 4. You know, all of the quizzes, they're fairly low stakes. They're worth 3 percentage points each, which means, you know, even if you totally do bad on a quiz and you get like 50%, that only affects your final grade, you know, 1.5 percentage points. Can we review our midterm before the final? Yes. I followed up with the students who hadn't taken their makeup exam, and they're not going to take the midterm exam. So okay, and is the final multiple choice again? Yes, the final exam will be multiple choice. So I will on Wednesday I'll go over a little bit more detail of the final exam, and then you'll take the final exam on Friday. Again, it'll be very, you know, similar to the way we did the midterm. I'll have two sessions, 10 a.m. and 10 p.m. And again, that's not our normal class time. We normally meet at 11, but we're meeting earlier at 10 a.m. Okay, so please keep that in mind. And yes, we will, it'll be multiple choice taken on the computer on CCLE. You'll log into Zoom, and that's how we'll proctor it. How much extra credit did quiz one? I think I said 1 percentage point, 1 percentage point in the final grade. And do we add that on top of our final score? Yeah, you know, I gotta figure this out exactly, but I think it's just like, you know, calculate your final grade, and then we add a percent. You know, I have to see how the gradebook settings work. I always get confused with the extra credit in the gradebook, but I'll try to put in the numbers so that it gives you an extra credit point. That's the plan. Okay. Are there any other questions? I don't know, I guess about class logistics, and I know everyone in the final week, everyone's kind of concerned about their grades and whatnot in the course. You know, I like to think myself as a fair instructor, so I'm not out to like, I don't know, like trap anybody with the exams or with the grades. How long is the final? It will, in my opinion, it will be comparable to the midterm, but just definitely focused on chapters 7, 8, and 9. You know, so yeah. I don't know how you feel, but I feel like chapters 8 and 9 are just a lot heavier in content, and, you know, in terms of like stuff. And so, you know, as far as like progress through the book, the second half, you know, is a lot slower. Like in the first half, we covered 6 chapters, you know, very quickly. And then just these past couple of weeks, we hit chapters, you know, 8 and 9. And in my opinion, I think those chapters require a little bit more time to go through. So yeah, the final will be focused on chapters 7, 8, and 9 as far as calculations go. There will be, of course, be conceptual questions from chapters 7, 8, and 9, and there's a fair amount of conceptual questions to cover there, and then, you know, a handful of definition / conceptual questions from you know, chapters 1 through 6. I'll try to get a better breakdown and a little bit more detail for Wednesday, and that's that. Okay, I have a question. Another question came in on the exams. If there's a commonly missed question, do you drop it from being counted? So I don't completely drop it. Like if I put in a question and then like 90% of students miss it or something, okay, or actually, let's see. Let's say if less than 20% get it correct, right? So if there's a question and there's 5 answer choices, just by random chance, I would expect around 20% of students to get it correct. And if less than 20% of students get that correct, then that's an indicator to me that this was either a trick question or you know, an unfair question or something. I don't like to completely drop it, because there might be a few students who actually knew the answer and got it right, and completely dropping it would be unfair to them. But what I will often do is I'll just make an adjustment for it, and I'll just kind of add that question's point value to everybody. So you know, if there's 50 questions and each question is worth 2 points, and let's say there were 2 questions that were, you know, quote unquote, you know, unfair, I might just go back and add 4 points to everyone's exam score. But that, I try to avoid that. I try to avoid writing unfair questions. I try to write questions that are fair. And on the midterm exam, there weren't any questions that kind of fit that category. And, you know, on the midterm exam, the median was, I forget what the median was, but it was like 90 something. So it was fairly high. So I'm hoping the final exam will be, you know, equally quote unquote fair, and that I don't have to make these kinds of adjustments, but we'll see. Yeah. And then, you know, again, you know, I shared the kind of the median scores. Well, let me go back. I forget. Okay, so the median was a 92, and the first quartile was a 78, and for the midterm. And, you know, if anybody, you know, struggled with the midterm, you know, I don't want anybody to feel bad or something, you know, and your performance is not, you shouldn't gauge your performance based on the performance of other people, right? So comparing yourself to others will lead to never being satisfied. So, you know, I want you guys to be content with what you have in life and what you've achieved on your own, and of course recognize that your life is far more than your grades and academic achievements. Okay. Anything else? So the final will be 2 hours long. My aim is to make it comparable to the midterm in terms of length, and so we'll see. Okay. So yeah, week 6, Monday. This is our final week. I hope you've enjoyed the. I hope you've enjoyed this class. This is it's intro stats, and I think I said right on the first day of class that the intro stats, when I took intro stats, it changed my life. Or maybe I didn't tell you the story. I don't know. That it changed my life, and now I came back to grad school to study statistics, and now I'm a professor of statistics, right? And I teach this class, and I enjoy it, and I hope, well, okay, I don't know. And I can't see your faces right now because I'm sharing my screen. So, you know, give me an icon of a yes or no or thumbs up, or put it in the chat. But I don't know, was the journal article at least interesting? And it was neat to see the application of statistics in kind of that, in like in a scientific setting, and being able to read. And okay, anyway, I hope that was, I hope reading the article was at least interesting, if maybe a little bit fun or something. You know, and maybe a nice change of pace from working with R. And you know, and I love working with R, but I know that love is not necessarily shared with everyone. Oh, and you read a book about p-hacking that mentioned p-hacking, and it was nice to see what they were talking about. Okay, yeah, I think definitely I recommend reading stats books, but of course I would. And I think it's you know, there's a lot of neat stuff. So okay. Well, I just thought maybe I'll run through a couple textbook problems. I got a couple emails and questions about chapter 9 stuff during office hours. It seems, you know, these couple problems. So I think I assigned 935 and 939. And so I'm doing 936 and 940 here, which are pretty much the exact same problems, but I'll throw them in the notes here. I'll kind of zip through them fairly quickly today. But if you have questions about any of this, don't hesitate to ask in the chat. Okay, so here it says, the weights of 4 randomly and independently selected bags of tomatoes labeled 5 pounds were found to be 5.1, 5.0, 5.3, and 5.1 pounds, right? So, you go to the grocery store and it says, this is a bag, 5 pounds of tomatoes, which is actually a lot of tomatoes. But, it's like, how do you know that, or it's more like 5 pounds of potatoes or something, but I think that was the other example, right? So, there's a bag and it's labeled that it weighs this much. And of course, it's not like you can tell the tomato vine or the potato plants to grow to this exact weight. And so, when they gather them into the bags, are they going to be exactly 5 pounds? No. And so somebody, I guess, took four bags and somehow they're random and independent and they measured them to be this, and is the average weight different from 5 pounds, right? And it would probably be a problem if the average weight was actually less than 5.0 pounds. But here we just want to know, is there evidence that there's a difference, and we're going to make a confidence interval, right? So for a 95% confidence interval, we first need to calculate our summary values, right? So our 4 values are this. We have 4 values, so n is 4. And then first we need the mean. That's really easy, right? You add up the 4 numbers, you divide by 4, you get 5.125 for the mean. And then the standard deviation, we need to get the standard deviation, and we have to use our standard deviation formula. And I think some students were kind of thrown off by this, in that, like we covered this way back in chapter 3, and we hadn't really touched it since chapter 3. So when presented with the question, find the standard deviation, or it didn't even explicitly say find the standard deviation. It was just kind of implied in that, the formula uses S and it's not provided in the problem. You had to calculate the standard deviation. And so, you'd subtract the mean off from each number and square that difference. You add those up, and then you divide by n minus 1, divide by 3. And when you do that, you get something, around 0.1258, right, after rounding. Okay, and so this step might have thrown some of you off. And so this is what you had to do, okay? Of course, we could have done this quite easily on R. You can just enter your 4 numbers into the computer, say find the mean of X and find the standard deviation of X, and you'd get the same numbers here, okay? And, on the final exam, it's open note, open book, and open computer. It is not, open talking to your friends. So you cannot talk to other people. But if you want to use the R to assist you in your calculations, that I do not have a problem with that. So if you want to do that, that's fine. So find the standard deviation. It's very easy. Just enter them and you get the standard deviation, right? Okay, we have 3 degrees of freedom, okay? Because it is n minus 1, 3 degrees of freedom. And so for a 95% confidence interval, our critical value, looking at 3 degrees of freedom, 95% confidence, is going to be 3.182. Oh, also in office hours, students asked, where did I get my table? I gave out the tables in week 3 under reference tables Gould, Gould being the author of our textbook. Reference tables. These reference tables are in the back of very back of your textbook in the appendix. Appendix A, there's tables, okay? There's the normal tables. There's actually binomial tables, which, we learned how to calculate the binomial table probabilities with a formula, but there is actually tables for binomial. And then the last table, or table 4, is the t-table, okay? Table 4 is the t-distribution tables, and that's where I got it. So it's available at the back of your textbook in Appendix A. It's also in week three of the of CCLE. I think so. That's where it is. Okay. So 3 degrees of freedom, 95% confidence, 3.182. Okay. All right. If our degrees of freedom is 49, should we look in the row for degrees of freedom equal to 50? Yeah. So there's in some textbooks will recommend always rounding down, but I think, yeah, I think you can just use the row that's the closest. Sometimes the I think our textbook actually recommends if you have over 40 degrees of freedom, you can even just use the like infinity degrees of freedom, which I don't know if I fully agree with that, but the difference between here's just the t-table alone. The difference between 40 degrees of freedom and infinity degrees of freedom is very small. It's like maybe a 2% difference or something. It's quite small. So so you know, maybe it's okay. But yeah, you know, I mean, the difference between 40 and 50 degrees of freedom, you know, what's that difference? It's very small. It's about a 1% difference. Okay. And then, you know, once you get over 100 degrees of freedom, definitely it's quite small. So yeah, I would just say round to the nearest. So if you have like 70 degrees of freedom, probably if you're not sure if you should round up or round down, I would say round down. Round down is a little bit more cautious. But if you have like 1,000 degrees of freedom, just go to 1.96. If you have, you know, 75 degrees of freedom, yeah, just go ahead and use 80 degrees of freedom. I think that's okay. All right. All right, so we've got a confidence interval. This is the formula, x bar plus or minus t star times s over the square root of n. This is the standard error over here. We're going to just plug in the values that we have. The mean that we observed is this. Our critical value t from the table is that. 3 degrees of freedom, 3.182. And then we plug in the s that we calculated and the square root of n. And you get 5.125 plus or minus 0.2, which gives us 4.925 to 5.325. Okay. And we say we are 95% confident that the mean weight of tomato bags is between 4.9 and 5.3 pounds. Does the interval capture 5 pounds? Is there enough evidence to reject a mean weight of 5.0 pounds? The answer is yes, the interval captures 5 pounds, and no, there is not enough evidence to reject a mean weight of 5 pounds because 5.0 is inside the interval. We don't have evidence that the mean weight is different from 5 pounds, okay? At least not based on these four bags that we've observed, right? Probably we would need to observe a lot more than 4 to make any kind of decent conclusion. Which is kind of interesting because as far as the 4 bags we observed, all 4 of them were over 5.0 or over. But even then we're not able to say definitively that the average weight is different. Sorry, that's my kid who's excited about these Easter eggs that they uncovered from months ago. Anyway, okay. So that's the confidence interval. And then we carry on with the hypothesis test. The hypothesis test will come to the same conclusion as the confidence interval. Well, I should say a hypothesis test carried out at the 5% level will come to the same conclusion as a 95% confidence interval. You know, if you do a hypothesis test at the 10% level, it will come to the same conclusion at a 90% confidence interval, and so on and so forth. Okay, so part A just says, should you be able to reject the null hypothesis that the population mean is 5 pounds using a significance level of 0.05? Okay, so without even carrying through the procedure, it's just asking us, can we make the conclusion, right? And so, so the answer to this is we should make the same conclusion, right? So a two-sided hypothesis test with a significance level of 0.05 will give the same result as a 95% confidence interval. And so our 95% confidence interval came to the conclusion that we cannot say that we have evidence that that it's different from 5 pounds, right? So we said we don't have evidence that it's different from 5 pounds. So our hypothesis test will come to the same conclusion. Without me even carrying out the hypothesis test, we know that it will come to the same conclusion. So the confidence interval does not provide evidence that the mean is different from 5 pounds because 5 is in the interval. And so if we conduct a hypothesis test, we too will also not find evidence that the mean is different from 5 pounds. Okay, so which means we would not reject the null. And at this point, whatever our p-value is, you know, we don't know the exact value, but we do know it's going to be greater than 0.05 because we did not reject the null. So we know our p-value is going to be bigger than our significance level, and so we would not reject the null. Okay. If someone says, what if you conduct a hypothesis test at alpha equal to 0.01? Okay. A 1% hypothesis test at the 1% level, we would also not reject the null, because even though we don't know exactly what our p-value is, just from this confidence interval, we know our p-value is greater than 0.05, so we know that it will also not reject if our significance level is 1%. Okay. On the other hand, if our significance level is 10%, we may or may not reject the null hypothesis because our p-value could be any number bigger than 5%. So it might be more than 10% or it might be less than 10%, and we're not quite sure what it would be. Okay. All right. So carrying out the actual hypothesis test, we would set up our hypotheses. And it's important to note that the hypotheses are always about the population parameters. So we use mu, not x bar. We would never write a hypothesis with x bar in it, okay? And when we're dealing with proportions, we never write a hypothesis about p hat, okay? Because x bar and p hat are statistics. We never write hypotheses about the statistics. It's always about the population parameters. So that's either going to be mu or p as far as this class goes. The null hypothesis always has an equal sign. So we'll put an equal sign in the null, and we'll have we have a two-sided test because we're just looking for a difference. So we've got mu equal to 5 versus mu not equal to 5. So these are the hypotheses that we will use. Okay. And then we'll go do our step 2, which is prep. So we'll use alpha equal to 5% because we're doing a 95% confidence interval. The problem tells us to use a 5% level. And then we check our conditions, right? And our conditions are met, okay? It said the problem stated that the sample of tomatoes were selected randomly and independently. I'm actually not sure how this could even be achieved in real life, but I suppose if the problem says, you know, we've done this and we've got a sample of random and independent tomatoes, then it's a random and independent sample. It is kind of like, as far as textbooks go, this is always a little bit of a cheat when they just say this sample was selected randomly and independently. In real life, it's really, really hard to get truly random samples. In textbook problems, it's easy. Um, it's easy to do something like that. It's a bit like, you know, in elementary school, it says like, you know, Sally has 15 apples and she eats 12 of them, right? But it's like, who eats 12 apples in one sitting? No one, right? But in a math problem, that happens regularly. And in statistics textbooks, random independent samples happen quite all the time in a textbook, but in real life, actually very hard. And so, so when you read a study, you know, even the journal article that I provided and stuff, you should always ask your question, you know, is this a random sample? It's probably not going to be a random sample. Is it reasonable to think that your sample is representative of the population? That's a little bit more subjective, and maybe even though the sample is not random, maybe it's reasonable to think that your sample is representative of the population. And so maybe it's okay to do this, all right? The problem also says to assume normality, okay? And again, this happens all the time in problems where you just say assume normality and you go, okay. This probably requires us to understand a little bit more the context of the data. The normal distribution shows up frequently, but it might not be safe to assume normality, okay? So anyway, as far as exam questions go, I'll make all of these things, you know, kind of explicit. In general, so on the exam questions, okay, if I ask you to carry out a t-test or a, you know, a hypothesis test in the exam, I will tell you that these conditions for the central limit theorem have been met. And then, you know, on the exam, I will probably have like a separate question that will describe some scenario, and I'll ask, you know, are all the conditions met, and is one of the conditions violated or something. I can provide a couple examples of that on Wednesday when we do kind of our review, so you can see what I'm talking about. But I won't have like a trap question where it'll be like, please carry out a t-test, and you know, what's the p-value? But the answer is, just kidding. You can't find a p-value because the central limit theorem conditions weren't met or something. I won't do that. Okay. And then the population would be all tomatoes, which would be a big population. I wouldn't even know how many tomatoes have ever been produced in life. I don't know. I don't even know when tomatoes were domesticated. I wonder what a wild tomato, you know, wild crops look like. It's very strange, right? Okay. All right. What's the probability of observing our data or something more unusual if the null hypothesis were true, right? That's how we're going to calculate the p-value, right? So what we observed in our data, we observed a mean of 5.125. If our null hypothesis back here, if this were true, okay, if mu were equal to 5, if the null hypothesis were true, when we take a random sample, we expect our random sample to have a mean of 5. We're observing a mean of 5.125. So the question is, what is the probability that a random sample has a mean of 0.1, that is 0.125 pounds or more away from what we expect of 5.0 pounds, right? So we observe 5.125, which is 0.125 pounds. So we want to know what's the probability of getting a sample that's 0.125 pounds or more away from the expected value of 5 pounds. All right. And so from the central limit theorem, we know X bar comes from a normal distribution where the mean is 5 and the standard error can be estimated with this 0.0629, okay? 0.1258 divided by the square root of 4. And we do this. Our test statistic is the difference between X bar and what we expect under the null hypothesis divided by the standard error. We get a test statistic of 1.987 with 3 degrees of freedom. Okay, I hope this is feeling okay. And so we're going to look for that number 1.987 with 3 degrees of freedom, okay? And I think using the t-table, you know, I had some questions about this during office hours, and what you're going to do is you're going to go into the row for 3 degrees of freedom, and you're going to look for this number 1.987. You say, where does it fit, okay? And it fits in between these two numbers, right? It's bigger than 1.638, but smaller than 2.353, okay? So our value of 1.987 is between these two columns. We go to the column headings, and that means our tail probability is going to be between 0.1 and 0.05, okay? And so because our alternative is two-sided, we're going to take our tail probability and multiply it by 2. So we multiply 0.1 by 2, we get 0.2. 0.05 times 2 is 0.1. So whatever our p-value is, we don't know the exact number, but we do know our p-value is between 10% and 20%. 10 and 20%. We don't know exactly what it is, but we do know it's between 10 and 20%. And so if our significance level is 5%, even though we don't know the exact p-value, we know it's going to be bigger than alpha. So we don't know exactly what it is. We know it's bigger than 10%, smaller than 20%. How does that compare to 5%? Well, whatever this number is, it's got to be bigger than 5%. Okay, so we don't reject the null. We don't have evidence that the mean is different from 5 pounds. Just kind of expanding on that. If the true mean is equal to 5, we would expect random samples to also have a mean of 5. Our sample had a mean that's a little different, 5.125 pounds. But the p-value says this is not unusual. This gives us no reason to doubt our null hypothesis. We would not reject the null. All right, and that's the steps. If you don't want to use the t-table, then that's you don't have to. Okay. The exam will be multiple choice, so my answer choices will be will probably be in this form where it'll be like the p-value is between 10 and 20%. Okay, I think that's a reasonable thing to respond with. But if you want to use R, you can also use R. And so our test statistic was 1.987, and we have 3 degrees of freedom. And so you can get the value from R using the PT function, right? So we learned P norm when we were dealing with the normal table, and here we can use PT for the t-table, and we type in 1.987 degrees of freedom equal to 3. Now R always gives us the area to the left, so it gives us something like 0.929, okay? So like something around 93%. That's the area to the left. So that says, you know, if you imagine kind of a normal looking distribution where you have 0 in the middle, and then on the positive side you have 1.987, everything to the left of that is you know, going to be over almost 100%. We're getting around 93%. Okay, so to get the tail area, which is kind of what the t-table reports, our tail area will be 1 minus that. Okay, so our tail area is around 7%. Okay, which aligns with what the t-table says, right? The t-table says it's going to be between 5% and 10%. We have 1.987, which is between these two numbers. So our tail area, our right tail probability is between 5 and 10%. And R is telling us the right tail probability is around 7%. Okay. And again, because we have a two-sided alternative, we're going to multiply that by 2. So I take 0.0705 and I multiply by 2, and I get something around 14%. So our p-value is around 14%, which means we do not reject the null. We don't have evidence that it's different from 5 pounds. And that also matches, you know, our earlier conclusion where we said the p-value is between 0.2 and 0.1. And that's that. Okay. Are there any questions on this? Do we feel good? no one's posted a question, so we'll carry on, and so today we'll look at the last section in chapter 9. In the textbook, some answers seem to add the values. Is that the same way for the exam? Add the values? I'm not sure what. I'll have to see what you mean by that. We'll look at the last section, 9.5. So the textbook, in my opinion, puts a whole lot of stuff in one section. And here I'm going to spend the rest of our lecture on just this one section. We're going to look at we're going to compare two population means, okay? And there are kind of two scenarios to consider, or at least be aware of, okay? Independent samples and paired samples, or we might call these dependent samples. So when we have independent samples, the two populations that we're looking at are independent, and the measurements that we've taken in our samples of data are unrelated to each other, okay? So it's like you have a sample of measurements coming from this group, sample of measurements coming from another group, and they're unrelated, okay? With paired samples, all the values that you've taken for one group or at one time are matched or related to all the values in the other group, okay? So for like examples of paired data would be you take a measurement on one person at the beginning of the study and then at the end of the study. So you have like a before and an after measurement, right? So it's the same person, but you're getting two measurements from that person, okay? So both of those measurements are paired together because they relate to the same person. Or perhaps, you want to take, get something on, like you're studying couples, and, you take, you ask, partner one some question, and then you ask the other partner, the same question, or, and you want to see, is there a difference between the two partners, et cetera, et cetera, et cetera, right? So, in that case, every measurement on one side corresponds to another measurement in the other group, or you could you might have like matched cases where you're trying to kind of control for different factors and stuff. That would be paired samples. So we'll take a look at these, okay? And for each of these, we'll look at a confidence interval and do a hypothesis test. So I guess we're technically hitting up four different things. The paired samples, this actually ends up being like a one sample confidence interval and one sample hypothesis test. So I think we can kind of cover this fairly quickly. So really the new topic today will be the independent samples. All right, so here's just a few examples of differences between independent and dependent samples. So here I've got a sample of randomly selected adults from the United States. The US are asked to rate the taste of a new soft drink on a scale to 10, right? So company is, like Coke or Pepsi or some other soft drink company is trying out a new flavor, and they want to see how do people feel about this. So they give it to some Americans, and they say rate this scale of 1 to 10. And then they also get some adults from the UK, England, Scotland, Wales, and Northern Ireland, and they're also asked to rate the beverage on the same scale, and they want to know, is there a difference, in the average rating of the US and the UK groups, right? So the two groups are independent of each other, okay? How the Americans rate the soft drink is not going to influence how the British will rate the soft drink. So these are independent groups, and so the two samples are independent. All right. Here is a different, similar but different scenario. In this case, we have paired data, okay, And here you can say you've got some randomly selected adults, and each of these adults are given 2 drinks. You've got drink A and you've got drink B. And they're each asked to rate each one on a scale of 1 to 10, okay? And you want to compare the average scores for drink A and drink B. So in this case, because the same adult is providing a score for drink A and a score for drink B, the 2 scores, they're related to each other because they're generated by the same person, okay? So each score for drink A can be paired with a score for drink B, okay? And so these scores are kind of linked to each other so that we say they're paired and they're treated as dependent or paired, okay? Is the distinction between, well, I'll assign some homework problems that also kind of cover the difference between what's independent and what's dependent, so you can identify, all right? But it's important that if data are paired, that we treat them as such, okay? Otherwise, you know, we can end up making the wrong conclusion. So when we make conclusions about the population means, okay, you know, we're looking at 2 samples of data, and you know, what we see in the 2 samples, based on what we see in the 2 samples, we want to make a conclusion about their respective populations, right? In particular, the question that we're asking is, do the respective populations have different means, okay? And so the picture that we have is, you know, here's this big entity, population 1. Population 1 has mean mu1, and population 2 has mean mu2, okay? So these are the 2 populations. They are too big for us to observe directly, and from each population, we're taking a small sample, okay, and this is sample 1. From population 2, we take a sample, and this is sample 2, okay? Sample 1 has mean x bar 1. Sample 2 has mean x bar 2, okay? Sample 1, we also get standard deviation 1 and sample size n1. Sample 2, we get standard deviation 2 and sample size n2, okay? And we only get to see the values inside the sample. We don't get to see what's in the population, all right? So, you know, when we take these samples, we only get to observe the values in the samples and their summary stats. We don't get to see the populations, but we want to make conclusions about the population mean mu1 and mu2, okay? Specifically, we want to know, what can we say about the quantity, or this difference, mu1 minus mu2? What can we say about the difference between mu1 and mu2 based on what we observe in our sample? So this quantity, mu1 minus mu2, represents the difference between the population means. And that's what we want to make a conclusion about, okay? And specifically, we want to know, could this difference, mu1 minus mu2, could that difference equal 0, all right? If the difference could equal 0, then that means the 2 populations could have the same mean, right? If there's no difference between mu1 and mu2, if mu1 minus mu2 is equal to 0, meaning there's no difference between them, then that means mu1 is equal to mu2, that the 2 populations do have the same mean, right? On the other hand, do we have evidence that mu1 minus mu2, that quantity, that difference, is that different from 0, okay? If we have evidence that mu1 minus mu2 is not equal to 0, then that means we have evidence that the 2 populations have different means, right? And so, so we're going to be looking at mu1 minus mu2, and we want to see, could it be 0, right? Is 0 inside the interval, confidence interval, or when we do a hypothesis test, is that quantity different from 0? Okay, versus, you know, do we have evidence that that difference is something other than 0? Okay, so this is the parameter that we want to estimate. Okay, we're not able to get the exact value because we can't see the populations directly. And so we're going to create a confidence interval for this that kind of represent plausible values for the difference. Okay, let me give you, I guess before we do that, let me give you the first quiz answer for today. First quiz answer is E. E as in elephant. E as in elephant. This is your last viewing quiz. I know it's a tiny bit annoying, but I hope. Well, I mean, you guys, I never had to worry about you guys. You guys consistently came to the live lecture, so so that's fine. But you know, for everybody else who's watching videos, I hope it's kept you all on track to watch the videos, because I know at least when I took an online course, it was very easy for me to slack off and not watch the videos, and then when it came to exam time, I was like lectures behind. And you know, it's miserable watching several lectures in a row. So I hope these quizzes have been helpful in keeping you on track. And I always appreciate, you know, the people who are attending live here. So anyway, first quiz answer is E as in elephant. And you know, let's okay, well, we'll do this and then we'll take a short break in a minute here. Okay, so before I get into the calculations, I'm just going to hypothetically make up thank you for saying they've been helpful. Just a fake confidence interval, right? So let's say we have two independent samples of adult men and adult women, and we measure the heights of men and women here, okay? And so a 95% confidence interval for the difference between mean heights, okay? So when we're making a confidence interval for mu1 minus mu2, we're making confidence interval for the difference between the mean heights, you know, that might go from, say, 4 inches to 8 inches. 4 inches to 8 inches, or 10 centimeters to 20 centimeters. Something around there, okay? And that's basically saying, we're basically saying the average height of men is somewhere between 4 to 8 inches taller than the average height of women. The confidence interval says nothing about the average height of men by itself or the average height of women by itself, okay? We're not making one interval for men and saying, you know, the average height of a man is somewhere between, you know, 5'8" and 6 feet tall, and the average height of women is somewhere between, you know, 5'2" and 5'6" or something like that. We're not making two separate intervals and comparing them. We're making one interval for the difference, okay? And so that difference, the interval for the difference might be somewhere between 4 to 8 inches, okay? And we would say I'm 95% confident that the average height, whoops, somehow I messed this up. Average height of adult men is somewhere between 4 to 8 inches taller than the average height of adult women, okay? Another way you could think of this is, you know, if there's quote unquote the average man, which, you know, is not a person that exists, but if you could just imagine the quote average man and the quote unquote average woman, again, these people don't physically exist, but if there were such a thing, you know, what's the difference in height between the average man and the average woman? And that difference is we're confident, 95% confident that it's going to be somewhere between 4 to 8 inches, that difference there. You know, again, it doesn't say anything about the average height of men alone, which is probably around, you know, 5'10", around 70 inches, give or take a couple inches. Okay, and the average height of women, which is probably around 5'4", give or take a couple inches. It's a statement about the difference, not about the individual means, but about the difference, okay? And in particular, what we're looking for is, you know, do we have evidence that there's a difference in average heights? And because 0 is not in between the ends of the interval, okay? And that the entire interval is positive, it goes from 4 to 8. 0 is not in between 4 and 8, okay? We have evidence that the difference between population means is not 0, okay? We have evidence that the difference is not 0, which means we have evidence that there is a difference between the population means. Okay, we have evidence that there is a difference between the average height of men and the average height of women. Okay, so we got a question and it says, does that mean we could use a confidence interval approach instead of a hypothesis test for seeing if there's a difference between two population proportions, what we did in chapter 8, or can we use the hypothesis test for two? Okay, so to answer your question, yes, you can use a confidence interval approach instead of a hypothesis test for seeing if there is a difference between two population proportions. And there actually is, the method is covered in the textbook, okay? The method is covered in the textbook. I elected not to cover it in this class because the formula for the standard error is different from the formula for the standard error with a hypothesis test. So, when after our break, we'll look at how to create a confidence interval and how to do a hypothesis test here. And thankfully, when we're comparing means, the standard error you use for the hypothesis test and the standard error you use for the confidence interval, it's the same formula. So as long as you recognize that you're doing, you have two groups and you're finding the standard error there, you know, you can use the same standard error. And I find it less confusing. You can, going back to your question. Okay, wait, hang on, are you okay? Damn it, all right. Okay, can you, oh yeah, what happened? You got hurt. Okay, can you go ask mom for help? Okay. All right, so what was I saying? Okay, so we have, yes, so you can take a confidence interval approach to see if there's a difference between two population proportions, okay? And that's, you can do that, but the formula for the standard error is different, and I didn't want to not confuse, but I didn't want to like add to it. And to be honest, I don't know, we don't often, well, so anyway, you can look it up. It's in chapter 8. It's the section I skipped in chapter 8 that talks about a confidence interval approach. So it's possible. Okay. Why don't we take a 5-minute break here, and we'll go through a couple examples, and we'll wrap up the day's content. Okay, so we'll take a 5-minute break, and we'll see you in a bit. Okay, so we'll go through the process of comparing means. We'll do independent samples before we do our paired data, okay? All right, and so I'll just throw the formula just straight out. So if you're making a confidence interval, this goes in the middle, the difference that you've observed, x bar 1 minus x bar 2, plus or minus t star times, and this formula over here, that's the standard error, okay? So the estimated standard error is this thing, S1 squared over N1 plus S2 squared over N2. And the margin of error is the t star times the standard error, right? So this part's the margin of error. Okay, we look up the critical value, the t star value, from the t-table. And the formula, so the formula for the actual degrees of freedom of two independent samples it's actually a complicated formula. So we're not gonna bother with it. We're gonna just use an approximation. And this is kind of like a cautious approximation. We're just gonna use n minus 1, and we have two n's. We've got an n1 and an n2. And so for the n, we're just going to use the smaller of n1 and n2. Okay, and that's kind of like the most cautious approach for estimating the degrees of freedom. So whatever your sample size is, you have two sample sizes, you choose the smaller one, and you use n-1 degrees of freedom. Okay. So here's just a silly example. So we're going to say a company gives its applicants a manual test for agility, maybe dexterity is a better word. And so the test counts how many, you got these, imagine like a preschool toy where you've got like the different circles or the different shaped holes, and you've got these different shaped blocks, and you've got to kind of match the blocks into the holes, right? There's also the game Perfection. I don't know if you guys played that, where it's like the thing pops up, right? You twist the timer and it pops up after a few minutes and stuff. Let's say we've taken data on 20 young adults and 15 seniors, and we want to say like, is there a difference in the kind of dexterity / agility of these people, right? And we're going to assume normality. Again, is this possible? Is it normal? I don't know, right? Is it possible to get random samples? I don't know, but we're going to pretend that we have these. Okay, so we're going to say the average number of blocks that the young adults were able to complete was 28.2 with a standard deviation of 4.3. Average number of blocks, I don't know why it says women. I think I copied and pasted something. And okay, the seniors were able to complete was 24.3 with a standard deviation of 5.7. Okay. All right, so I've got, all right. So does the confidence interval provide evidence that there's a difference in the average number of blocks completed by, should say, young adults and seniors? Sorry, I think I copied and pasted the problem and I changed the group names, but I didn't catch them all. Okay, so there's a confidence interval. So we're going to make a 95% confidence interval for the difference between means. Is there evidence of a difference between the young adults and the seniors? Okay, so here are the values that we've measured. Okay, for the young adults, the mean is 28.2. This should be x2. For the seniors, the mean is 24.3. Standard deviation is this, 4.3 and 5.7, 20 and 15, okay? For our critical value t, we have n-1 degrees of freedom. So we're gonna use the smaller of n1 and n2. So we're gonna use 15, 15 minus 1. We have 14 degrees of freedom. We go to our t table, looking at 14 degrees of freedom, 95% confidence, we're going to use 2.145. Okay, so now it's just a matter of plugging in all of these numbers. 28.2 for x bar 1 minus 24.3 for x bar 2 plus or minus the t star 2.145 times s1 is 4.3 squared, n1 is 20, s2 5.7 squared divided by n2 15. You do all of this. This difference is 3.9 plus or minus 2.145 times the standard error, which is 1.758. So we're going to get 3.9 plus or minus 3.77, and our confidence interval goes from 0.13 to 7.67. So we're saying we are 95% confident that on average, young adults can complete between 0.13 and 7.67 more blocks than seniors on average, okay? And because 0 is not within the bounds of the interval, we do have evidence that there's a difference between the average number of blocks completed by the two groups. Okay. And that's it. This is just a formula, and you know, it's open note, so you know, I would put a star on this page or something that says, you know, 2 independent samples confidence interval is on, you know, slide 52 or something, slide, or, you know, 23 or whatever, okay? So, so this is what you have here, okay? So that's it for confidence interval. And the bold part, right? Okay, so what we're looking for is there evidence of a difference, okay? And so this is a confidence interval. Keep in mind, let me just go back. When we make the confidence interval, it's a confidence interval for the quantity mu1 minus mu2. It's for the quantity, the mean of population 1 versus the mean of population 2. And we want to know, could that difference equal 0? Could mu1 minus mu2 equal 0? So, you know, when you make a confidence interval for like one sample and we say like, could that, like for the tomatoes, we said, could the mean equal 5? We're looking to see if 5 is within the bounds of the interval, right? Does our interval contain the number 5? Here, we're making an interval for this quantity. This quantity represents the difference between the means. And we want to know, could that difference be equal to 0? Could the difference be equal to 0? And so we're going to check to see if 0 is in between the ends of our interval, okay? And because 0 is not between the ends of our interval, that means we do have evidence that there is a difference. Does it matter? Oh, okay, this is a good question. So does it matter that we did seniors minus young, okay? Like what if I labeled, so I apologize for the typo here. What if we labeled the groups differently, right? Like what if seniors was group 1 and young adults was group 2, okay? If you did that, what would happen, okay? This would become 24.3 minus 28.2, okay? It's probably worth, I'm gonna go ahead and just add another slide here. Okay. What if we swap group labels? What if seniors was group 1 and young adults was group 2? Then what would happen is the difference would be we would have 24.3 minus 28.2, and the difference would end up being negative 3.9 plus or minus this, which would be negative this, and we would get negative 7.67 to negative 0.13. Okay, and the answer, like if we did a direct okay, so our conclusion would be ever so slightly different. We would say we are 95% confident that on average seniors can complete between 0.13 and 7.67 fewer blocks than young adults on average. Okay, this has the same meaning, but kind of our point of reference has changed. So one conclusion is we're saying young adults can complete more blocks on average than seniors, and then in the other we're saying seniors can complete fewer blocks than young adults. Okay, so so choosing what you label to be group 1 and what you label group 2 doesn't actually make a difference. Okay, as far as the interval goes. Okay, I guess technically this would have been swapped over here and this was swapped over there, but so if you so you would just get the negative version, right? So the only thing that changes is that we're subtracting 24.3 from 28.2, 24.3 minus 28.2. Okay, we're swapping these two numbers. This part all remains the same, and so this part becomes negative. Okay, so we get negative 3.9 plus or minus this thing. Okay, this quantity is still the same, and so this becomes negative 7.67 and negative 0.13. So you're going to make the same conclusion, just instead of saying young adults can do more blocks than the seniors, we're going to say seniors can do fewer blocks than the young adults. And I think that's fine. Okay. And again, same conclusion. 0 is not within the bounds of the interval, so we do have evidence that there is a difference between the average groups. Okay. All right. So now we'll go ahead and do the hypothesis test. Okay. And so the confidence interval provided evidence of a difference. We're going to expect the hypothesis test also to come to the same conclusion and say there is evidence of a difference. Okay. And so especially if we did a hypothesis test at the 5% level. All right. So again, we're going to use mu, never x bar. We always have an equal sign in the null hypothesis. And so in this case, our null hypothesis is that the two means are equal. Mu1 is equal to mu2. Is there a difference between means? The null hypothesis states that no, there's no difference, that the two means of the two populations are equal to each other. And then the alternative is that the means are different, okay? And so this is our null and our alternative hypothesis. Okay. We should check conditions. It should be young adults and seniors were selected at random. I have to go through and clean all of this up. The problem tells us to assume normality, and so that condition's met. And as long as we have big populations, we'll be fine. Okay. So what's the probability of observing our data or something more unusual if the null hypothesis were true? So we're going to compute the p-value. Okay. If the null hypothesis were true, we would expect the two random samples to have the same mean. Okay. And in our data, the two samples don't have the same mean. Okay. One is 28.2 and the other is 24.3. So could this difference be the result of randomness? That's our question here. Right. Specifically, what's the probability that two random samples have means where the difference is 3.9 or more? That's what we want to do. So our standard error, this is the same standard error formula that we used for the confidence interval. This is what we get. When we plug in the numbers, we're getting a standard error of around 1.758. And our test statistic is going to be the observed difference, observed versus expected, right? The reality versus what we expected. So we observed a difference of 3.9. We're expecting a difference of 0 if the null hypothesis were true. And then we're going to divide by the standard error. So this becomes the difference that we observed is x bar 1 minus x bar 2, a difference of 3.9, okay, minus 0. You can technically leave off the minus 0, okay, divided by our standard error of 1.758. We're going to get a test statistic, a t, of 2.218, okay, and we're going to look at n equal to 14 degrees of freedom, right? So using the smaller of n1 and n2, we have 15 minus 1, 14 degrees of freedom. And we're going to look for this value, 2.218. So when you go to the t table, if you go to the row for 14 degrees of freedom, okay, we're going to look for, 2.218. Somehow I got this wrong here. 2.218, and we see 2.218 is in between these two values, 2.145 and 2.624. Okay, so 2.218 is in between these two values. So you go to the column headings, and we say that the corresponding tail area is between basically 1% and 2.5%, between 1% and 2.5%. Okay, And because our alternative hypothesis is two-sided, our p-value is 2 times that tail area, right? So when we double this, our p-value is going to be between 5% and 2%. We don't know exactly what it is, but we do know it's more than 2%, more than double this, but less than double this, less than 5%, okay? So even though I don't know exactly what my p-value is, I do know it's between 2 and 5%. So we know it's less than alpha 5%, right? If alpha is 5%, we know our p-value is less than that. So we reject the null hypothesis, and we have evidence that there is a difference, which is the same conclusion that we made when we created a confidence interval, right? So if the two populations have the same mean, we would expect random samples drawn from each population also to have the same mean, okay? And our samples have a difference of 3.9, and the p-value says this is unlikely to happen by random chance alone. So the fact that we did observe this unusual result provides evidence that our null hypothesis is wrong, okay? Okay, and it's possible that the null hypothesis is correct and that we've committed a type 1 error. That's also possible, but based on our significance level, you know, we would reject the null hypothesis. So so the process is very similar. The only, you know, the difference is that how we calculate our t and our standard error is just is a little bit different. Okay. All right. Do we have any questions here? Is this feeling okay? Okay. Let me give you your second quiz answer. Your second quiz answer is B. B as in bear. Okay. Your second quiz answer is B. Bear, ball. That's what we've got here. Okay. So let's do paired samples, and this will be our the last topic, and that will be it. Okay. So sometimes we collect measurements that are related to each other. So common examples are before and after studies. You can do couples or twin studies, also matched pairs, things like that, okay? And the important idea is that every measurement from one group is matched with a measurement in the other group, okay? Yeah, viewing quiz 2 and 3. Yeah, so the second viewing quiz answer today is B, B as in bear. Second quiz answer is B, okay? The first one was E. E as an elephant was the first one. The second one is B as in bear, and then I'll give you the third one, and I guess at the end of class. Okay, so every measurement in one group is matched with a measurement in the other group. Okay, so that's the key idea here. Okay, and when we do paired samples, we actually don't care about these individual. We don't actually care about the before measurement and the after measurement. Okay, we actually only care about the difference. Okay, so you might see. So this is like a very silly, simple data set where I only have 4 observations here. Okay, and this is, you know, the textbook has this problem, but they did it with I think like a much bigger sample. So is there a difference in a person's ability to smell if they're sitting versus lying down? You know, I don't know if you're lying down, can you smell things versus when you're sitting? I guess you feel like you're more alert when you're sitting, but anyway. So I guess they have some kind of smell test, and I don't even know how this works, but they did a smell test and people get some kind of score, okay? Some kind of score on their smelling test. And so person number 1, they gave the smelling test when they were sitting, and that person scored a 13.5 when they were sitting. And then when they were lying down, the person scored a 13.25, okay? And then person 2, when they were sitting, they scored at 13.5, but when they were lying down, they scored lower at 13. Person 3 scored 12.75 sitting, and when that person was lying down, they scored 11.5, okay? And then person 4 scored the same in both, okay? And so the important thing is that every sitting measurement is paired with a lying down measurement, okay? It's not that we took 4 people and gave them the smelling test when they were sitting and we measured them, and then we took 4 separate people and gave them the smelling test when they were lying down, okay? Because if you did that, then there's no reason why, you know, this person's measurement should be linked with this other person's measurement, right? Because you could probably link them to any of the other ones and it wouldn't matter, okay? And well, I guess you could have designed the study so that, you know, each person comes in with a partner, and, you know, maybe these are people that live together, or, you know, they're brothers and sisters or siblings or something, and you're kind of comparing that. You know, if the study is designed in such a way that every measurement over here is explicitly linked to a measurement in the other group, then you'd have a paired samples, okay? But here you've got the same person measuring, giving a 1 score and a lying down score, right? So an important fact is that if it's paired data, you're going to have the same n for the sitting and same n. Like here we have 4 values here and 4 values here, right? If we had 4 values here and 5 values over here, then it can't be a paired study because every measurement can't be paired with another one. So we've got every value paired with the other, and you know what? We don't actually care about these individual values. What we're going to do is we're going to generate a column over here called the difference, and that becomes the only column that matters. So we're just going to say, all right, what's the difference between these two things? 13.5 minus 13.25, what's the difference? And we get 0.25, 0.5, 1.25, and 0. Okay, so we create a column for the difference. And now that we've created this column, this is the only column that matters. Okay, this is the only column that matters. We don't care about what's in this column. We don't care about what's in this column anymore. Okay, so we calculate the mean and standard deviation of this column. The mean is 0.5, standard deviation is 0.54, right? If you were doing it in R, you can create this vector. Once you create the difference is 0.25, 0.5, 1.25, and 0, and you can say what's the mean of X and what's the standard deviation of X, right? If you have a problem, and sometimes this happens in the homework and stuff, or maybe even on the exam, it might say, you know, here are the 3 columns, and this is the mean of the sitting column, this is the mean of the lying down column, and the mean of the difference column. And here's the standard deviation of sitting, standard deviation of lying down, and standard deviation of the difference, okay? Even though it gives you the mean and standard deviation of the other 2 columns, just ignore them. They don't matter anymore. Once you have the difference column, that's the only column that matters. What happens in this original 2 columns don't matter, okay? We basically just have one sample, and it's this difference column. So now that we've reduced the data to 1 column, we create confidence intervals and hypothesis tests in the exact same manner that we did for 1 sample, okay? So here we've got n-1, 3 degrees of freedom. Formula for a confidence interval for 1 sample is this. So, you know, we've seen this already. You just plug in your numbers. You got 0.5 plus or minus 3.182. Standard deviation of 0.54 divided by the square root of 4. So our standard error is this. So we have 0.5 plus or minus 0.86. Here's our confidence interval. And so the conclusion, does this interval provide evidence of a difference? Okay, and so now we're just asking, is the difference column, could the average equal 0? Okay, and so right now we say we're 95% confident that the mean difference in smelling scores of sitting and lying down is between 0.36 lower and 1.36 points higher, which is a strange thing to say. oh, this doesn't all fit. But basically, because 0 is in the interval, um, 0 is in the interval, it's plausible for the mean difference to be 0, meaning that it is plausible that there's no difference between the mean score for sitting and lying down, okay? So we don't have evidence that there is a difference. Okay. So the interval contains 0. 0 is in between the bounds of the interval. So we do not have evidence that there is a difference, okay? Because we're looking for 0, and it's in between our interval. Okay, if we want to do a hypothesis test, it's the same process that we go through if we have one sample, okay? So we set it up with one sample. We're checking to see if mu is equal to 0 versus mu is not equal to 0, okay? And the same process as before. One thing to note is that the problem didn't tell us to assume normality. So we only have a sample of 4 people, and so any size sample is large enough if it is normal. And if the population is not normal, then we don't have a large sample, and we could be making a mistake, right? So it's just, a lot of times you just have to think, like, what assumptions am I making when I go through these calculations? And in this case, we're kind of assuming normality. And maybe it's a safe assumption, maybe it's not. All right, we'll go through for the p-value, all right? And we would expect the mean to be 0 if the null hypothesis were true. We would expect x bar to be 0. We're getting an x bar of 0.5. Could this happen by random chance? So you go through the calculations. So your standard error is s over the square root of n. You punch this in, 0.5 minus 0 divided by 0.27, you get a test statistic of 1.852. I'm kind of going through this very quickly because I feel like we've done this many times already. So I'm hoping it's okay, but if you want me to slow down, tell me to slow down, okay? And so we get this test statistic t. What do? We look this up in the t table with 3 degrees of freedom, n minus 1 degrees of freedom. So we're going to look for, 1.852. Sorry, I keep having the wrong thing. 1.852 is in between 1.638 and 2.353. Okay, so we look at the column headings, and we see that our corresponding tail area is somewhere between 5 and 10%. We have a two-sided alternative, so our p-value is 2 times that, and our p-value is going to be between 10 and 20%. So our p-value is between 10 and 20%. We're not going to reject the null hypothesis. We do not have evidence that the mean difference is something other than 0, okay? And we have no reason to suspect that sitting or lying down makes a difference in smelling ability, okay? And I know I went through that a little quickly, and I have some typos that I've got to go through and correct. But I feel like we've seen the t-test for one sample, multiple times already. And so I hope that it was okay that I went through this quickly. We have a question. Do we have a lab this week? No lab this week. So today I asked the TAs to go through some homework. They'll do that or answer any questions. On Wednesday, I'll kind of go over what you can expect to see on the final exam, and it'll be a review session, and we'll do some extra problems and things of that nature. And then on Friday, you'll have the final exam. So so that's about it. That's it for new content. This is all that we will cover in our class. We've covered through chapter 9. We're not going to have time for chapter 10, but we rarely get through chapter 10 in a regular 10-week course either. So I don't feel too bad about that. And I don't know if anyone's brokenhearted about that. So, so that's what we have. Oh, your last quiz question is B again, as in bear. B as in bear or ball. That is the last question. Last quiz question for the viewing quizzes. And that's that. I hope you've enjoyed the course more or less. There is course evaluations, and I appreciate you guys responding to those and filling those out. And I hope you've enjoyed the course so far. And that's it. Wednesday's review session is optional. You can attend or you don't have to. But it's intended to help you out and help you prepare for the final exam. So, but that's optional. So, oh, and thank you for your compliments of saying you've enjoyed the class. And yeah, so if I could ask you a favor, I know I'm asking a lot of you. I give you like homework and all of these quizzes and labs and stuff. I know I'm asking a lot of you, but if I could ask you just a personal favor in terms of filling out those course evaluations, that would be great. Stats made your summer great. It's surprising to hear that, but I'm happy to hear that as well. I have not. Do we have discussion on Wednesday as well? I leave that up to the TAs. I think the TAs will hold discussion on Wednesday to just as a review session to help you out. But I'll give them the autonomy. You know, if they feel like canceling discussion, you know, that's up to them. But I think they're there. We're here to help you guys learn and just make sure you do well in the class. That's what we want. Okay. So you know, I'm on board. That's why I'm going to have the review session. The TAs are also on board in terms of just, we want you guys to do well, right? We want you guys to do well. So we're trying to give you as much as possible. Okay, yeah. Oh, well, thank you guys so much for saying thank you. I'm the one who needs to be thanking you. You have taken the class and, you know, despite the not ideal situation of distance learning and having to learn through Zoom and, you know, us being separated, I appreciate you guys still enrolling and coming to class, especially you guys who have been faithfully tuning in to lecture. Thank you so much for that, and enrolling and registering for the class. You guys give me a job that I love, and I'm so thankful for. So thank you for that. Last quiz answer was B, or is B. The last quiz answer is the letter B, as in bear or baseball, and that's what we have. And that's it. You have a quick, maybe foolish question, maybe. All right, go ahead and ask it.
So this was a question about the textbook problem 9.36.
Oh, yeah. Okay, yes. Thank you for bringing that back up. Okay, so this is what we have. Yes.
So I'm sure I'm just missing something here, but if T star was 3.182, why is it the mean plus or minus 0.2? Where did 0.2 come from?
Oh, if you multiply this all together, I think, I'm pretty sure. So if I do 3.182 times 0.1258 divided by the square root of 4, so divided by 2, you get 0.2.
I had just skipped and put T star directly in there. Okay, I get it.
Okay, that's all. Okay. All right, well, thank you guys. Have a good day, and we will see you guys maybe on Wednesday, if not, definitely on Friday for the final exam. All right, and again, thank you guys all for saying thanks, and we'll see you either on Wednesday or Friday.